All right, this is the third lesson out of chapter 24, and we'll be in section 24.2 talking about forces caused by magnetic fields. Now, as a quick review, and I know some of you may have just watched the other video, there are rules which govern what happens around a wire. If I have a wire and I have electricity flowing through this wire, I point my thumb in the direction of current flow. That would be positive. If it was positive down here, my hand would go this direction. I wrap my fingers around, and my fingertips will show you the direction of current flow. And it's a circle. And that the tips of your fingers would be pointing north. And so you have something like this around that wire. This would be in the case of my thumb pointing toward me and my fingers going around. If we have a coil of wires, what we find is that inside of here, both of these, if I put these on exactly the same direction, I kind of messed that up before, and I put that in the center through this coil, all of the magnetic fields will line up in the same direction. And what happens then is if you grasp that coil with your right hand, fingers in the direction of current flow. So let's say it's positive here, I would bring my hand this way and my thumb would point north. If the current was flowing the other direction, my thumb would point the opposite direction, but it would still be north in that case. Now, there's one other thing that happens, and that is that because you have magnetic fields, and magnetism is a field force, if I take a current-carrying wire, which has a magnetic field around it, and I put it into a magnetic field, just like two magnets will exert a force on each other, those two, the wire and the magnetic field of the magnet will interact with each other. And you will have a force, either attractive or repulsive, that will take place. That force is going to depend upon the strength of the magnetic field of both the wire and the magnet itself. Before we go on, I should mention that magnets have a constant, just like we would have with gravity or with when we were talking about the field strength of a electrical field. And the symbol for magnetic field strength, if you remember electrical field strength, it was a capital E. That was the strength of the field. This is magnetic field strength. The symbol is B, and the unit is a Tesla. And the symbol for Tesla is a T, a capital T. And it is named after Nikola Tesla, who did a lot of the early work on understanding the connection between electricity and magnetism. Now, let me show you the connection, then I'm going to talk about that third right-hand rule. I have here, and it's a little hard to see it, I'll move it this way so you can see this a little bit better. I'm going to turn this down just a bit. This is a little contraption I built. I've got two wires here. They're connected up to my, my voltage source. And this is a copper wire that's hanging from there. It's free to swing back and forth. Don't want those really there, but not much I can do about that. Now, this magnet is not attracted to that wire at all in any direction because it's copper, and magnetism doesn't react with copper. But if I put this and do this now there's current flowing through this, and when I bring this over, you should be able to see it move. It does not, it's either attracted to the magnet, or if I turn it around, it'll be repelled from the magnet, depending. There you see it being repelled. Turn this around, you can see it being attracted to the magnet. there is a force, a connection between those. And depending on whether the magnetic field is one direction or the other, it's going to attract, and it will be attracted to that. It'll be pulled. There is a force that is on it. That is actually fairly significant when it comes down to applications, which we'll talk about in the next video. Now, there is a rule called the third right-hand rule, which allows us to figure out what the direction of force will be. And the right-hand rule says something like this. If I take my wire and I pretend this is a wire, I put it in my magnetic field. If my fingers point north, my thumb is in the direction of current flow. My palm will tell me what happens to the wire. In this case, this wire will get pushed up. If the current flow direction changed, it would be this way. Pretend this is still over here, and that would get pushed down. In this case, you saw that the wire was being attracted, and that's because this magnetic field is this direction. So this is putting out a magnetic field, and I'm going to take that wire out. If this was my palm, I'll do it this way so you can kind of see it, a little hard. If my thumb, the current was going toward the whiteboard, and that was my wire, and this is my magnetic field, and north is up, this is going to get pushed this direction, and that's what you saw happening. On the other hand, if I was to turn the direction of the current around, now that wire is going to get pushed out this direction. Most of the time, when we do this, they will draw it something like this. They will put a magnet. This is how motors end up working. And they'll do a horseshoe magnet, a magnet which is, you've seen them before, I'm sure. You take a regular magnet, you bend it up. You have a north end and a south end. So it actually could look something like this. All right. What I'm doing is showing just the ends of this. So this is actually going back like this. If I put a wire in here, and let's say this is north and this is south, we have a magnetic field that goes straight across there. If that wire is coming out of the board, I have a magnetic field that goes around like this. Now, if you look at this, and it's a little tricky, these two are in the same direction, these two are in opposite directions. As a result, these two field lines are opposites of each other, and this will get pushed out of that. It's being repelled from here because those are the same magnetic field, opposite magnetic fields, and will get pushed out. And this wire essentially will just get pushed straight down. So that would be the picture of something which was a horseshoe magnet this way, a wire coming straight through, and that wire is going to go down. Now, if we had turned this around and we put north and south, and I had it this direction, this doesn't change. But now as we go around, this magnetic field, this one was coming out of the board, that's going into the board. This would be like this, and this would get pulled up out of there. If I had the wire in here, between here, and I had same thing, then if this is coming, this will get pushed up out of here. If this wire, on the other hand, was perpendicular, by the way, the force, it's perpendicular motion. If I had this wire going this direction, and this was north and this was south, now, if I was to take and do this, my fingers would go this way, my thumb would come this way, and this wire would actually get pushed out this direction. It would get pushed out from the whiteboard. It is always a perpendicular motion to that magnetic field. Right? Now, there is an equation that tells us what the force will be. It's my favorite equation in all of physics. It is force is equal to Bill, where B is in Teslas. And by the way, I should have mentioned that 1 Tesla is 1 Newton divided by amp meters. So if you have a wire that is 1 meter long and you have 1 amp going through it, and that produces 1 Newton of force, that would be 1 Tesla. If you had something which was 10 Newtons with the same amount, it would be 10 Teslas and so on. Notice though, it's interesting, it's a magnetic field and yet it's defined by its current and its distance that it travels. Now, your book blows this. They write this F is equal to ILB, but I like it this way because it just sounds like the name Bill. And so force is equal to Bill. And because of that, we can rearrange this any way you want to. But if they were to say, let's just do a simple problem. You have a 10 Tesla magnetic field, and you have a current of 2 amps and a length of 80 centimeters. And the question is, what is the force on that wire? Well, we just plug in the numbers. The one thing is that has to change to 0.8 meters, and the force then would be 10 Teslas times 2 amps times 0.8 meters. And this is really newtons divided by amp meters, 20. This would be 16 newtons on that little wire. Obviously, we could rearrange it. Oftentimes, you want to know what the magnetic field strength is, in which case it would be this. So if they were to ask, what's the magnetic field strength, the magnetic field, this might say intensity of a magnet, the way they actually test it is to take the force and put a current, or measure the force on a current carrying wire. And so let's say that we had that question, what's the magnetic field strength if we have a force of 2 times 10 to the negative 3 meters, or newtons on, well, let's make this bigger. Let's make it 2.5 newtons on a wire which has 1.5 amps and a length of 20 centimeters. In that case, our magnetic field strength would be 2.5 newtons divided by 1.5 amps, and 20 centimeters would have to change to 0.2. And we would end up with 2.5 divided by 1.5 divided by 0.2, and we'd end up with a magnetic field strength of 8.3 Teslas. So it's pretty simple. Now, one other interesting equation. Let me see how much, yeah, we've got time. I'm going to erase this over here. It turns out that a charged particle, like an electron, will have a force act upon it. By the way, that's how an old TV used to work. If you watch that video in the third left-hand rule, he showed an old video. But they used to actually, to make a TV, they would shoot electrons and put it through a magnetic field, and those electrons then would veer, because even though it's a single electron, it is a charged particle that's moving. The real intent of this is not that it's a wire that's experiencing the force. It's the electrons in the wire that are experiencing the force. And because we have a wire, we can quantify how many electrons go through. That's what current is. But let's say we had a single charged particle. Let me go back to here. F is equal to BIL. If you look at I is coulombs per second, and length is meters. And I could simply redo this. I is coulombs per second, and length is in meters. If I were to rearrange this and do it this way, this is the charge on the particle, not the charge, the charge, electrical charge, and this is velocity. And so there is another equation, which is B times QV, or might be QVB, however they write it, and this would be the force on a charged particle. So let's say that we had a magnetic field strength of 15 Teslas, and we had a Q, the charge on some particle of 1 times 10 to the negative 6 coulombs. And let's say those particles are traveling close to the speed of light, 3 times 10 to the 8 meters per second. What is the force that that particular electron? Remember, an electron is very, very small. What would the force on that electron be? The force would be equal to 15 Teslas times 1 times 10 to the negative 6 coulombs. And by the way, it can't be going that. I said 1/10. That would be 3 times 10 to the 7. 3 times 10 to the 7 meters per second. And we would end up with 450 newtons, I think, if I've done that math in my head correctly. 15 times 30. Yeah, 450 newtons. By the way, that's very unrealistic. You have 450 newtons on a little particle. The acceleration would be faster than, well, this is a bad problem, the way I have it set up. Well, this would be actually a lot of electrons. So those are the two parts of this. Now there's one other part to section 24.2, which is, we'll get to in the next lesson, and that's some applications of this. And what you're going to do for me on this, we're going to do at the this chapter 17 through 25 odd. Those are practice problems, so you'll have the answers for these. And then we're going to do 72 through 80 even at the end of the chapter. And I'll get you those answers. I'll put them up with the assignment that's online. So that finishes really most of the chapter. The rest of it are just some interesting applications of all of this. And we'll get to that, of course, in the next video.